Fine, go ahead and read, let's read this problem, and then I'm gonna have you guys, see if you can try it. Part A should feel familiar, review, Pythagorean theorem. Then part B, we gotta create a trig equation. We'll find the derivative and make the substitution. All right, go ahead and try that. The key's on the back, but I want to see how much you can get done on your own. The handout up here. You go. hopefully part A feels familiar with the Pythagorean theorem. The only thing that I keep that we make sure that we know is that is x and y positive or negative. So it's not the direction that matters. Going north doesn't mean it's positive. Going east doesn't mean that it's positive. It's because you can imagine x and y increasing over time. That's what we want. That's why I want to be positive. Now, if the cyclist was here and moving towards the intersection, then we are going to expect dx dt to be negative, right? So you want to make sure that you can convince yourself, imagine this problem in motion and convince yourself whether the dimensions are increasing or decreasing, and let that guide whether you want your race to be positive or negative. Okay, so Pythagorean theorem, to get to that z value, 13, and then the rest just plugging into our derivative equation, right? Makes sense that d to dt is positive as well. X and y are, the two cyclists are moving away from each other, so that distance between them is going to be growing. Okay, part B, at what rate is theta changing at that moment? So we know that we're looking for d theta dt. So to get to that portion of the problem, we first have to create our trig equation. So we're going to rely on tangent because we have information about x and y, and all three sides are changing. So there is no constant. There is no constant in this equation, right? Cyclist A is not standing still. Cyclist B is not standing still. So because of that, we have to make sure we hold on to the variables, which means that we're going to be forced into push control. F prime g minus f g prime all over g squared. So tangent theta becomes secant squared theta d theta dt. F prime times g minus f g prime all over g squared. So dy dt times x minus y times dx dt all over x squared. Everything on the right side we can plug in from part A, but we have the thing that's different about this process is we have to find the replacement from secant of theta. Secant theta, we go to our second triangle, we build out that triangle here. This moment in time, we have the dimensions of this triangle. From there, we can find secant of theta. Secant is hypotenuse over adjacent. Put that into our equation. And then now we're just trying to get it down to solve for d theta dt, right? The calculus portion is done. Now we're just trying to combine values and get our d theta dt down to a numeric answer. D theta dt is always going to be radians per time unit. So in this case, radians per hour. Any questions here? Okay, page 3 in your packet. talk about, I crossed off 1 and 2 because I wanted to do one that I think would be helpful for Monday, being able to involve inverse. Solve for t. For tangent of 2 pi t over 3 is equal to 1 on the interval from 0 to 2. We're going to do this by hand. So let's first involve inverse to get this isolated. We're trying to solve for t, so we're going to try to move things away from the left side all over to the right side to isolate t. But what can we first move here? Yeah, so when that tangent moves to the other side, what does it become? Inverse tangent. Okay. So this is asking the question, when does tangent of theta equal to 1? When is tangent of theta equal to 1? Yeah, in that pi over 4 family, right? So pi over 4, where else? By pi over 4. Now, because we're dividing by 2 pi over 3, some of these values may shrink. And if they do, we want to make sure that we have enough that we don't miss out on some solution. So let's go past 2 pi and list out potentially more than we need, and then we'll know whether we're on the right track once we get everything cleared out. So if I want to add 2 pi to get more coterminal angles, that's the same thing as saying plus 8 pi over 4, right? All right, so what's next one up here? Another variation of pi over 4 is, there you go. 9 pi over 4, right? 8 pi over 4 plus 1 pi over 4. Okay, and the original third quadrant here, what's next? Okay, so we have all of our, we converted inverse tangents into radian measures. Now I can solve for t. So to solve for t, I can divide by 2 pi over 3, which is the same thing as what? Yeah, times 3 over 2 pi. So let's multiply this out. What do we get here? 3 over 2 pi times pi over 4, what does that become? 0 over 8, yep. The pi's cancel out. 3 over 2 pi times 5 pi over 4 becomes 8. Next up, 27 over 8. Last one up, 39 over 8. Okay, so now we go back and look to see if maybe we have more than enough, which is fine. More that it's good to have more so that we can just remove the ones that we don't need rather than not have enough and not know that we didn't go far enough. So we only want to go from 0 to 2. So which ones do we keep all of these? This first two, right? 15 over 8 is still slightly less than 2 because 16 over 8 is 2, and 27 over 8 is definitely more than 2. So we can just keep these two down. Okay, any questions here? I created some, or I left some blank pages in the packet. And I wanted to use these spaces to have us try some more problems that are related to 1 and 2, inverse trig derivative and implicit differentiation. So if you guys can turn to page 28B, it's near the back. I have a couple of blank pages for us to add some problems. Go ahead and copy this down here. Dy dx, find dy dx, y secant 2y squared equals cosecant cubed to 2 pi squared x minus y plus 4x minus 3. Okay, I do want you guys to try this on your own, but I want to make sure that we're on the right track here. There's 3 things that I want us to make sure that we see before we jump into our derivative step. Can you list those 3 important concepts we have to make sure we include here? Implicit, because these have a bunch of y's. How many dy dx's do we expect to show up? 3, yeah. Good. And where's the product rule going to take a role? Yeah, we know this is 2 expressions. Okay, good. One more thing. Chain rule, right? You got to get that bracket cube to show up. We can clearly see the outside inside portion. Go ahead and try it. I'm going to work on it as well. Okay, after this step, we're just grouping all the dy dx terms together, right? We're expecting 3 dy dx terms. Group them together on the left side, factor dy dx out, and then solve for dy dx. Don't need to fill anything out. I'll do a little bit of dy dx by itself, that's all I need.
This group is put together and combine y, 4y, you get 4y squared. Why is the ui have to be like a plus instead of a minus?
Oh, you mean this part of it?
Yeah.
That is from this over here.
Uh,
Yeah, I moved this one over here. So I know I ran out of room, so I'm figuring I can find it on the other side. On the right side of the equation, that minus 1 plus 4.
Did you like separate it where like all the ui dx functions are on one side and
Yeah, that's what I do, yeah. So that we can want all these dx terms together so that we can factor it out and eventually get the factor. Good. Any other questions? Okay, next page. Let's see if we can practice an arc trig derivative rule. Okay, what's involved here? Product rule, yeah. And then this is not cosecant to the -1 power. This is not chain rule here. Well, not in the sense that we raised, there's no bracket, right? This is arc secant, arc cosecant.
There's a log. Exponential.
Where do you see that?
Sine x.
E is just a number, treat E like pi.
Okay.
So what's the root of EX? Just E.
Just e.
Yeah, oh, to the constant. Yeah.
Just like running the number. Yeah.
It's the number, right? Like 3x. Like pretend like it's 3x and you're finding the root of cosine of sine of 3x. All right, check my work. You guys get the same thing. Yeah.
Where's the one there?
Fixing prime. Right, so the derivative rule for arc, so speak then. Every one of the rules has u prime up top, right? It's just, there's a negative, looks like arc secant, but there's a negative in front. Got to take into account another negative in front of this derivative, so that's why the two negatives are positive. Okay, page 6. Number 5. Does anybody still need this page? He is on page 12. Yes. Um, wait, say it again. Arc cosine is 0 versus the inverse. Yeah, so, well, when you do inverse cosine, this is basically saying, this represents theta. So you're asking cosine, in other words, this is basically another way of saying, when is cosine of theta equal to 0? It's rearranging it, but it's basically asking the same thing. But here you're looking not for the ratio, you're asking for the radian measure here. Okay, I'm listing out more. Essentially, I know that I'm going to shrink these here once I divide by 2 or multiply by 1/2. So want to make sure that I can get all the values.
You actually give us like a.
Right, but I think it's easier to use inverse cosine here. So, but yeah, I mean, you can also go through that way as well. But I like to do the inverse procedure because if it was sine of 3x, then we want to really use inverse, right? This double-angle identity is really not going to help us too much. Okay, we're only going from 0 to pi here, so which one do we not need? Yeah, these are out. Slope sine line. Let me test pi over 2 into the derivative. Cosine of 2 times pi over 2, that's the same thing as cosine of pi. Cosine of pi is negative. Okay. What do you expect at pi over 4? Relative max. 3 pi over 4, there's a relative 10. Okay. Find those ordered pairs. Um, this is 6 pi over 4. 6 pi over 4 is same thing as 3 pi over 2. Sine 3 pi over 2 is. Okay. We have our relative order pair for relative max. We have our order pair for relative min. Let's move on to second derivative. Okay, so 2 cosine 2x becomes negative 2 sine of 2x times 2. Okay, I'm gonna test pi over 4 here, sine of pi over 4 times 2, that's sine of pi over 2. Sine of pi over 2 is 1 times negative 4 is negative. So concave down, followed by concave up.
Wouldn't we not, like, wouldn't pi not be and zero not be ones because they're n?
Yeah, they're endpoints, so they're just duplicates, but I'm still gonna put them onto my sine line. Yeah, but you're right, they're just duplicates, so I can just ignore the, just rely on my endpoints. So what do you expect at pi over 2? Inflection, okay. Okay, so we got through the hardest part of the problem. The rest of it is you also want to find your order pairs at your endpoints. And then go to your graph and start putting it into your graph. Okay, the key is on page 12. Guys, I'm finishing up on the morning review. I haven't quite finished it yet, so I will send out reminds to you when I have the worksheet and the key completed. So that you can, if you want to work on that over the weekend, you can, and then I will go over that morning review worksheet on Monday. Okay, so I'll send out the worksheet and the key, hopefully by this afternoon, if not, then tonight. All right, can we just vote?
Possible one left night.
Oh, good.
That's like all the right, so.
Everything went, according to plan.
Well.
Yeah.
Back to. You guys do another topic. You should have.
You can take it anytime, I just, got it, come in, or Wednesday, the Friday, half day, so, yeah, but I'm free, you can come in. As long as you finish whatever you want to finish.
And like, our teacher, our director, he did like a surprise saxophone full and everyone was crazy.
Wow.
It was really cool.
Good turnout.
Yeah, it was great. It was great for now. People were like almost sold out. As far as like I was helping to clean up. It's insane. We never had that many people on stage, like over 100 people on stage.
Wow.
The massive cleanup operation.
Is it the biggest concert of the year?
Well, the biggest is the spring. Not spring. Like in terms of like people, yeah. We never had that many personnel. It's insane.
That's impressive that everything went so smoothly, like,
Oh, yeah.
moving parts.
Yeah, our director's great at like. I don't know anybody else now. Yeah.
That's sure stressful.
Yeah, it is pretty stressful. Try to help them the best I can. Bill's got to win. That'll be the Chiefs.
Patriots look a lot better because of the quarterback, right?
Yeah, I mean, I was happy to see it. I was happy to see it as well. But like, I still wanted the Patriots to lose. No, I still wanted the Patriots to lose because, you know, during my.
Yeah.
They're like, it's actually better for us than the Steelers. Oh, he's gonna, can't lose another game. We have our playoffs start this weekend.
It does, it really does.
Yeah.
You have to
Chiefs
win.
on the ring.
Huh? Yeah, beat Chiefs. I mean, he's gonna afford to lose.
He can be fine. I mean, he'll be 8-5, so it'll be still, they'll still make the playoffs. Yeah. Like, we have to win. And it's really even hard because they're coming off a loss during the long week too.
Oh, that's right. I don't want that too long.
We don't need break.
Yeah.
Put ourselves in a situation where we can win with this sort of thing.
I know.